tonight's gonna be a quiet one. Okay, I understand. If there are no questions, which is, I'm trying to figure out if I should say which is fine or which is concerning. It's somewhere in the middle of those two. I will say this, I had no plans to necessarily focus on this, but somebody had a question about, oh, let me make sure this is all about me. Hold on. There I am. It's all about me. Somebody had a question about this one. It's a pretty good question. Can somebody see, like, what's the main difference between this type of problem and this type of problem? 33 and 37. What's the obvious main difference? And then we'll talk about the implications. The implication.
Radius is squared.
Yeah, one of them has got the radius squared. Now somebody else tell me, what is a possible implication of that? What does that mean about this guy?
So r squared cannot be negative.
It was, Bowen. Huh? Good. I love it. R squared can't equal a negative number. So anything that has a negative output here, and of course cosine can be negative, obviously, that just goes out the window. Bye. And let me also remind you, oh shit, what's over there? Hold on. Let me make sure I'm not going to share somebody's quiz. Okay. As always, if you're doing your homework and you don't have sitting next to you the wonderful frickin' reference sheets I give you, right? You got your trig identity sheet, you got this sheet, and what about this sheet? This side, okay, we did this side, right? And you also got the book, of course, but it's so much easier to graph something if you know what the family of curves looks like, right? So these guys look like this, right? For example, and these guys are clovers, oh, and that's a circle, okay, and then so forth, right? Then your butt graph and your spirals and your ovals. All right, don't worry, this is not a standard, by the way. This is not a standard one. I think I just put this on here to be, to show you the generalization of a lemniscate. All right, anyway, sorry. So if you keep this sitting next to you, or the book where they go over the different shapes, I still need to see work for you. I still need to see a table of values. But if you know what the shape is supposed to be, you know if you're in the right direction. You know if you're getting the points that you're supposed to be. Does that make sense to anybody? This is how we graphed anything in the history of your math life. It was easier to graph if you knew what it was supposed to look like. Okay, all right. Okay, so I'll just assume that that was amazing and very helpful. All right. If I don't hear anything, what I said was amazing and very helpful. Okay. Let me see, what else did I want to show you? Was there something else? I did open up the solutions video for the practice quiz. So that's up there now. You can access that. Okay. If there's no other questions on any homework or anything, we're going to get right back into the next thing.
So when will be the quiz due?
Oh, I don't know. Probably Saturday morning. Does that sound right?
Yes.
I'll open it up Thursday night and I'll make it due early Saturday morning. Okay, if any of you like to go wild on Friday and do pre-calculus quizzes late into the night on Fridays, I don't know, that's a wild lifestyle. You got to slow that down when you get older. All right. Okay, anything else, guys? Okay, all right. Let's see. I was prepared to do more examples if anybody had questions, but apparently I don't need to. So let's see. Today, as I promised, we are going to get into polar form of complex numbers. So let me do this. Before we do this, we're going to review a little bit of complex numbers. We've already done complex numbers before. Let me turn off my, oh shit, Jeff. What have you done? I pushed the wrong button. Oh, good. Okay. There. All right. Now. I need you to understand this. Every function that we've ever looked at in this class, we could go back and use complex numbers as inputs and accept complex numbers as outputs. Now that would make them so much more difficult to work with. I don't know if you remember the video I showed where the guy picked it up, it was all colorful and shit. You'd need some way to do that. Okay, that's all right. Anyway, so what we're going to do now is not that. We are going to develop another way to write complex numbers. And let me give you a little teaser as to what we'll be able to do once we get these written in a different format. So this is kind of cool. All right, not this. This is statistics. Okay. Oh, geez. Why are you over here? All right. Oh, I see. Oh, why is this so dark? I know. Gotta turn this dude on. I got so many lights in this place. It's crazy. All right, there we go. Complex number. Can somebody give me an example of a complex number? Let's see if I have any smart asses here today. Let's find out. Anybody? Or somebody writing it in chat, maybe? I don't know. I can't see chat. Nope, nobody's doing anything. Where are you guys at? Oh, there you go. Say it again.
I.
9?
I.
Okay, that'll work. Let's see, I can't make that work. All right. Sure. So an example is I. Somebody else give me a different example. Do you guys remember? What is this? This is part of a complex number. What is this specifically called? What kind of number is this? It starts with the letter I. That's one way to remember it.
Imaginary number.
Imaginary. I love it. Thank you. Complex numbers. Does anyone remember what those look like? They have an imaginary part and they have something else.
A real part.
A real part. Kick ass. So they're a combination of, so here's an example. I can't use Roman numerals, I guess it's a bad idea. Another example would be 4 minus 3i. Oh, there you go. I see it in chat. Thank you. Another example is 5 plus I. Kick ass. Now, we've done this part already. We've talked about this part. Can we graph this? What would it look like? What we decided to do is this will be the real axis and this will be the imaginary axis. So can you plot this number in the on the set of axes? Can you plot this number in that plane? Yes, you can. Right, you would go 4. And then down 3. Bam. So this is 1, 2, 3, 4, 5. This is negative I, negative 2i, negative 3i, negative 4i. This is negative 1, negative 2, negative 3. This is I, 2i, 3i, 4i. Okay. Geez, on yours, it looks like it's down there. Geez. My perspective is all off. Okay. Right, is that cool? 4 minus 3i? No worries. Doesn't that look like a normal XY point? And we know it isn't, but doesn't it look like a normal XY point? Of course it does. Right? What did we just do to have a different way to identify an XY coordinate, an XY point? What did we just do? We went from using rectangular XY, and we decided instead we could use polar. I love it. So all this is going to do is this is an accepted way to represent a complex number, right? It ends up looking like a polar possibility, because can't you identify an R, and can't you identify a theta? Yeah. So the beautiful thing is we already know how to convert. So the thing you got to realize is 4 minus 3i becomes, in a way, it becomes the point 4, -3. We know it isn't. We know it's this, but in this format, it looks like this. All right, I love it. So can somebody tell me what is the angle? How would you figure out the angle that we're dealing with?
Tangent.
Yeah, so you would do inverse tangent of, so let's see,
-3/4.
it's 3/4, right? Y over x, that's what tangent is. All right, can somebody give me I should have picked a better, it doesn't matter, Jeff, it's fine. Give me a rough estimate of what that is. Throw in the old calculator.
-0.64.
Sounds about right. Did anybody else get that same thing? Anybody else do it?
Yes, same thing.
Same thing. Okay, I love it. Let me see what's going on here. Poor little thing. Okay. Okay, so that's that. Now, what about R? What's R? How do we figure out what R is?
5.
Yeah, this is nice because it's 3, 4, 5. That's easy. And of course, it would be x squared plus y squared equals r squared, but we know a 3, 4, 5 triangle. So R is 5. Now, I want you to realize something. Is this a point? This right here, is this a point?
Yes.
No, it is not a point. It is a number. It is a number. It doesn't have two parts. It's not a number, comma, number. It is a number. All right, I don't want to go too deep into the technical details here. I'm not trying to rewrite 4 minus 3i into r theta because this is not a point. It's a number, right? It's a number we're not used to dealing with. It's a number that doesn't fit on a number line because it needs an extra dimension to handle the imaginary part of it. It's freaky. We're not used to it. So that's not the point. So what the hell's the point then, Jeff? I don't know. So we're going to take 4 minus 3i, and that's going to equal r cosine theta plus I sine theta. All right, let me see if I can. What's all right? What's a better way? Let me think. Oh, anyway, what would r cosine theta be? It would be 4. Are you guys with me? I know theta is gross, isn't it? Isn't theta gross? Who gives a shit? What's r cosine theta? It's 4. I know it is. So this equals r cosine. Oh, what's r? Sorry. R is 5. R cosine of negative 0.64 plus this would be sine of theta, but it would be times I plus I sine of negative 0.64. Oh my goodness. So what we are doing, I really want this to make sense. Is this, are you guys, the x piece, of course, is r times cosine theta. The y piece is r sine theta. That much we've known for a while, right? Not forever, but for a good little while. So on the surface of this, I really want to address this. If you understand what I just did, it seems kind of stupid, right? It does, because 5 times this. Can you guys put this in the calculator? What is 5 times this? Somebody just do that in the calculator.
4.1.
4.1. So that points to squares.
4.01.
Say again.
4.01.
That sounds better. Okay, I was gonna say, because otherwise this is like a bad approximation. It's 4, isn't it? That piece, this is this. And if you do sine of this times 5, you'll get 3, -3. All right, so what we just did. This is the let me think, how do I say this? This is not a terribly difficult part. So the neat thing about complex numbers is they do look like XY points. We can use polar kind of stuff to talk about them, but they're not points. They are numbers. So I have a real part plus an imaginary part. But now I can use it in terms of cosine and sine. That is lame on one level. I really want you guys with me. Let's do this. In general, what we're doing to introduce something new, we use the letter Z for complex numbers. Kind of makes some sense, right? X and Y are normally thought of as real numbers, so we use the letter Z is the main thing we use for complex numbers. If Z equals A plus BI, I can rewrite that in the form R cosine theta plus I sine theta. I'm not sure why you're using a bracket, Jeff. It's all right, dude. There you go. Where theta is the inverse tangent of B over A, just like we did down here. And R is A squared plus B squared square root. So this is the same stuff we used before. This is just polar stuff, which makes sense because when you graph a complex number, it looks like an XY plane. So maybe I can use the polar stuff to do something. Okay. Maybe. Now, let me show you what we are going to be able to do in a little bit. Let me erase this here. Yeah, I'm going to erase all this stuff. You ready? I'm going to do another example, I think, with some nicer numbers. Eventually, we'll be able to do something like this. What do you got, Jeff? 2 plus 3i to the 11th power. And I mean, do this quickly. How would we have to do this now? What would we have to do if I ask you to do this by hand? What would you have to do? Anybody? Nobody? What would you have to do to figure this out by hand? What's happening out there? What do you have to do to figure this out by hand? What do you have to do?
Foil.
Yeah, you got to write it twice and multiply out. So how would you have to do this one by hand? You have to write it 11 times, multiply the first two, and then multiply what you get by the next one, and then multiply what you get by the next one, and then multiply what you get by the next one, and then go insane, and then go insane, right? Okay. The point at which you go insane is different for different people, but it would happen somewhere on the way to 11. So we're going to develop a way to do something like this quickly. And what about this? What about the 11th root of I? We're going to be able to figure this out. We don't even know what the shit the square root of I is. Damn, we're going to be able to figure that out. Let me stop for a minute. And now I know some of you guys are probably right now looking at your screen and saying, I don't want to know those things, Jeff. I don't know if you think this is enticing, but I don't want to know those things. And I'm like, all right, then you fail that part of the class. So you do want to know it on some level. You do. Hopefully some of you guys are like, I would kind of like to know what the square root of I is. It is something. It is equal to something. Okay. I like it. I like it. I like it. Now, let me see. What was I gonna? Oh yeah, let's do one more example. I think a nice concrete example, and then we'll work on the little teasers I just did. We're working on getting there. So what if I have this? This one here. Yeah, let's do. You could do it, Jeff. Sure. Yeah, sure. All right, that's fine. Let's do this. So I got to figure out. So I want to put it into this format. I don't know why I keep trying to use brackets. Oh well. So I got to figure out what theta is. I got to figure out what r is. So go ahead and take a minute, figure out what those two are. We're treating this as if it's x, and we're treating the coefficient here as if it's y. That was neat. All right. Now this is one you should know or have a way to figure out. Let me show you a little trick. I don't know if anybody's noticed this before. Isn't this, I have no idea if anybody's memorized this or how you guys do this, but watch what I can do. Can't I throw a little over 2 into both of those? Right? Isn't that the same thing? It isn't tangent sine over cosine. And if I really am smart, I can leave the negative with what it really should be on. Okay, let's see if anybody gets what I'm trying to do for you. So this is the answer to this is the angle where the sine is 1/2 and the cosine is negative rad 3 over 2. Does that make, I don't know. I have no idea if that makes sense or if anybody kind of looks at it that way or anything. I don't know. So where's sine theta equal to 1/2?
Pi over 6.
All right, pi over 6. And where is cosine theta equal to negative rad 3 over 2 at the same time? So it's pi over 6 or, so it could be pi over 6 or it could be over here. In the second,
5 pi over 6.
5 pi over 6. 5 pi over 6 is where sine is 1/2 and cosine is negative. And can you tell me real quick, what quadrant is this in? Negative rad 3, 1. Isn't that in the second quadrant, right? All right, let me stop for a minute. So now we got the angle. So how do I get r?
Square root of minus square root of 3 squared plus 1 squared.
And this is beautiful, right? This will be 3 plus 1 is 4. Square root of 4 is 2. That's nice. So I can rewrite this complex number in the form 2 times cosine of 5 pi over 6 plus I sine of 5 pi over 6. Now, again, I don't want to take away from the usefulness of this, because this is unbelievably useful if you go one more step. But if I just stopped here, this would be complete and utter bullshit. I really want to address, if anybody noticed that this is true, this would be total bullshit. I gotta do one thing for myself before I go crazy. All right, let's see if that works. Bam, okay. Because what is 2 times cosine of 5 pi over 6? Well, that's cosine of 5 pi over 6 is negative rad 3 over 2 times 2 is negative rad 3, right? And then what is sine of pi, what does that say, Jeff? 5 pi over 6. What's sine of 5 pi over 6? That's 1/2 times 2 is 1. So on one level, I have taken this perfectly fine number and made it worse. Yes? And again, I'm trying not to shit on this. I'm not shitting on this because we don't stop here. If we stopped there, we would never have done this because it's bullshit. Would you rather write 1 or 2 times sine of 5 pi over 6? Which one's better? 1, I think, is better, right? So the true usefulness of this is what we do with it next. Okay. So let me see. All right, I'm going to erase all this. You guys ready? Maybe I should keep this. Well, all right. Yeah, maybe, all right. That's kind of gross. All right, no, I'm not good. All right. Maybe I should. All right, cool. I will. Plus I equals 2 cosine 5. Okay, that's just okay. I'm gonna erase all this. Now, let's look at something like this: a plus bi to the let's just say to the well, let's just say squared. Why not? So if I rewrite this, it would be r cosine theta plus let's do this, I sine theta. That's kind of funny, Jeff. The one time it would make sense to use brackets, you don't. All right. All right, now go with me on this. All right, this is kind of neat. In fact, can you guys, let's see, can you guys go ahead and do this? Go ahead and so I'll tell you, this is r squared here, right? So then I have to do this cosine theta plus I sine theta times cosine theta. Go ahead and FOIL that out. All right, let me catch up to you a little bit. R squared cosine squared theta plus 2I sine theta cosine theta, right? I sine theta times I sine theta is I squared sine squared. What's I squared?
-1.
-1. So I get minus sine squared theta. Does anyone notice something about this piece?
Sine 2 theta.
Yeah, so 2 sine theta cosine theta is the identity for sine of 2 theta. Now somebody else tell me, what about cosine squared theta minus sine squared theta? What is that?
Cosine 2 theta.
Yeah, Rio's like, I'm tired of waiting. Is anybody else out there? So by this point in the class, you should be able to identify cosine squared theta minus sine squared theta as cosine 2 theta. You have to be able to identify that. You should know that right now. Okay. So this, the real part, is cosine 2 theta. And the imaginary part is I sine 2 theta. Now, look what happened. Look what happened. When I squared this, the r squared, but what happened to these guys? It's like that went inside. Wouldn't that be cool if the same thing happened for third power, fourth power, fifth power? Wouldn't that be exceptionally cool? So what I'm going to do, instead of, because this gets kind of gross if I want to keep going this way. So we're going to, I just wanted to lay this groundwork for you. It does look like powers might act nicely, but let's take a step back. All right. I don't know if you guys followed what just happened. We're hoping that a third power would end up being 3, 3, 3, and that's it. Because then I could do an 11th power really easy. Yes? That would be amazing. I wouldn't have to multiply shit out. So what I want to do is, let's say I want to do a plus bi times c plus di. I want to multiply 2 different complex numbers. Yeah, if it could work. And you know it will, or else all this is for naught. So go with me here. So I have 2 different complex numbers, correct? So this one is going to be, let's call it Z1. So that's going to be R1 cosine theta 1 plus I sine theta 1. Amazing. So what's this guy going to be? I just don't know, Jeff, man. Z2 equals R2 cosine theta 2 plus I sine theta 2. And then what am I going to do with them? I'm going to multiply them together. So I'm going to do Z1 times Z2. All right, anyway, so let's see what we get. This will be R1 times R2. Okay, all right, R1 times R2. And then I have to FOIL this stuff out, right? I get cosine theta 1, cosine theta 2, plus I sine theta 1 cosine theta 2 plus I sine theta 2 cosine theta 1. Minus, because it'll be plus I squared. So it'll be minus sine theta 1 sine theta 2. Okay, now this one looks a little bit, why does this definitely looks worse than the square we just did, but it's going to be a more useful building block. This looks worse because we have different angles and different R's and shit, right? Because they were 2 totally different complex numbers. They're going to have different radii, they're going to have different angles. So everybody still semi with me? Was anything I just did really hard? No, it's a bunch of frickin' foiling, right? And you have to remember that I squared is -1, but you know, no big deal. Now, I don't know, has anybody gotten their identity sheet out since the last question I asked you? You might want to have that sitting next to you. Can someone identify the real part? Is there an identity related to this?
Cosine theta 1 plus theta 2.
Yes. So that's the real part. That's those 2. Bam, 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 bam. And now somebody else maybe tell me for the imaginary part. I take an I out. Sounds painful. What's the? Is there a what do you Sine, cosine plus sine, cosine. Doesn't that sound like another identity? This one was cosine because he's an asshole, right? Cosine, cosine meet first. That's why it was cosine of the sum. Made this a minus because he's an asshole. What's this one related to? Somebody else?
This is sine plus sine. Wait, sine A plus B. I'm not sure.
Yes. So it's sine of A plus B. So theta 1 plus theta 2. I like it. So now, now I can kind of build. So now this is a quick way to see, what if the thetas were the same? What if theta 1 equal theta 2? We would get 2 theta in here and 2 theta in there. We would get the same thing we just got. Because if these were equal to each other, that's like squaring this one. Yes? Maybe. But what do you think would happen if I threw a Z3 in here? It would just add in here. You could actually go through the whole thing, you could see it happen, but it would end up just adding in here. It's kind of cool because, I don't know if you guys are with me at all. Let me see, how can I say this really quickly? How would I do Z? I don't even know. Please be with me, everybody. Please come with me. Come with me. I already did Z1 times Z2, didn't we? So if I multiply, what is theta 1 plus theta 2? What is it? Is it a stick? Is it a rock? Is it a salamander? What is theta 1 plus theta 2?
Angle.
An angle. It's some other angle, right? So this is a radius times cosine of an angle plus I sine of an angle. Isn't this just another complex number, of course? So if I multiply it by another one, it's just going to do what any complex numbers would do. This multiplies by the radius. This adds to the angle. This adds to the angle. So now I've got a much, now I can kind of build on this. Let me see, I'm going to erase all this. Let me see if I can capture this. Maybe I'll keep this last thing here. Okay. So what I'm saying is, if I put another thing in here, oh God. So it's basically just taking this times Z3. The result would be R1 times R2 times R3 times cosine of theta 1 plus theta 2 plus theta 3 plus I sine of theta 1 plus theta 2 plus theta 3. All right. Whoa. Yeah, but exactly. Exactly. That's why this is a little gross. It's a proof, and you can tell it's a proof because I don't have specific angles. This is any angle, any radius, any complex number. This is true for. So we have proven that 3 complex numbers multiply with this, but we've effectively proven that however many complex numbers, I just have to do this. I just multiply the radii together, add their angles together, and throw them in. Bam. Now stay with me. So this actually helps us prove, what if all of these equal each other and all of these equal each other? Right? What if these were actually the same complex number? So I'm basically doing a plus bi to the 3rd power. And again, I have no idea what percentage of you are still with me out there. If anybody's still with me out there, thank you. Come on now, we can do this. Okay. If these were all 3 the same number, which means the radii would be the same and the angles would be the same, wouldn't this just equal r cubed times cosine of theta, 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 3 theta plus I sine of 3 theta, just like we hoped. Exactly like we hoped. Thank God. Okay. Maybe. So therefore, if I have a plus bi to the 11th power, that will be r to the 11th cosine of 11 theta plus I sine of 11 theta. So let's attack a real concrete thing. Yes? Anybody want to attack a concrete thing? Normally, this is where students are like, yes, can you give me some freaking numbers, Jeff? Holy shit. I'm over the A, B, C, R, theta, 1, 2, 4, 9. Get out. All right. So I'm going to erase all this. You ready? Oh, let me make this even more general. A plus bi to the nth power is r to the nth power times cosine n theta plus I sine n theta. Thank you very much. All right. Beautiful. That is a thing of sheer beauty. So let me give us, oh shit, I was going to use that. Am I going to use that right now? Poor little thing. Yeah, let's use it right now. I like it. 2r cosine. Wait, what was this? Oh yeah, that's a bracket. There you go. Okay. So we're going to use this guy. So I want to do, was this negative? I think so, yes. I want to do negative rad 3 plus I to the 8th power. Okay. So what I'm going to do instead of that is I'm going to rewrite. I know it's this. Let's see, this should be interesting. All right. Somebody help me out. 2 to the 8th, is that 256? Do you see? So now I'm going to apply this idea. So now it'll be 2 to the 8th. And let me just apply the idea. Times cosine of 8 times 5 pi over 6. Is that cool? Because it's cosine times n theta. So 8 times theta plus I sine of 8 times theta. All right, let me stop for a minute. Hopefully you're back with me because this is so kick-ass. Would you want to do this by hand? No. What if you could do this? Oh, yes, that's fine, please. That's awesome. It's making an 8th power become a multiple of 8. That's beautiful. All right, I'm going to erase this down here. This is really important right there. Erase this here. Maybe I'll leave that last line. All right. So I think this is 256, right? Anybody wants to help me out? No? All right. And then I get cosine of 40 pi. Oh, let's see. Let's reduce this. So that'll be 4/3. So that'll be 20 pi over 3 plus I sine 20 pi over 3. Can you guys, isn't this kind of a silly thing here? Can somebody, do you understand what I'm saying? Isn't this like a lot of rotations? Do you understand what I mean when I say that? Because 6 pi over 3 is 2 pi. So let's see, how many 2 pi's can I take off of here?
6 times.
Yeah. So then what's left? So I take 18 pi over 3 off, and I'm left with 2 pi over 3. So is everybody cool with that? That's the same thing. That's the same. This is the same. Cosine of this is the same as cosine of this. Because that's just this with a bunch of extra rotations. So it sounds like this angle with a bunch of extra steps. That's true. Same thing here. Is it? You guys, that's the coolest part of this, is that this, you can use a reference angle or a coterminal angle, whatever you want to call it. It becomes a million rotations. You take it down to less than 1 rotation. Okay, maybe. Now somebody help me out. What is the cosine of 2 pi over 3?
Over 2.
Yeah. So but it's
Negative.
negative. And what's the sine of 2 pi over 3?
3 over 2.
3 over 2. So now if I multiply this in, this will be half of 256. This is 128, negative 128 plus 128 I rad 3. Is that cool? Half of 256 times rad 3 times I. Oh boy. Oh my God. Now let me show you the coolest thing that you're gonna hate me for not showing you earlier. That was relatively quick, wasn't it? I mean, that was relatively, is this quick? No. Is it quicker than writing this 8 times and multiplying it out? Yeah. Yeah.
I just have a little question.
Yes, yes.
You can do this only with the imaginary number, right? No, like x plus or something.
All right, how do I say this? Any mathematical object that when that has a representation that looks like an XY plane, you can use something similar to this. That's a very vague answer, and I'm sorry, but
Okay, yeah.
there might be other mathematical objects that, like complex numbers, I can represent on something that looks like a plane. That would then have an angle and have a radius. Yeah. That sounds like a very math teacher answer, and I'm sorry. Now, let me show you something really, really, really cool. All right, everybody come back. If you're somewhere else, come back. I'm gonna show you how to do shit in the calculator and just get it done, all right? But you know me, right? Pushing buttons is not showing your work. So if answers come out of nowhere, all right. But I do want to show you this, just in case you don't know. Does anyone know how to use the graphing calculator and put complex numbers directly in? Do you guys know how to do that? So we see, I've had mine. Here we go. So see where it says down here? So if you go to mode, I think you can even do it without doing this, but I'm just going to do this just in case. And do you see down here above the decimal, there's an I? So let's do this. Negative square root of 3 plus I to the 8th power. That's the one we just did, right? Of course, you're going to do that to me. Oh, that's dumb, Jeff. So look what I did. This is so awesome. This shows you, I don't care how good at math you are, I put the minus button instead of the negative button. Okay. Oh, why is that so gross? Oh yeah, because, of course, duh, I forgot the square root of 3. So help me out. What is 128 times the square root of 3? That's where that came from. So that is the same thing we just got. Who's talking to me? Where's the I? Oh, the I is above the decimal place. See it hiding right there? So again, if I want to use it, I can put in there. And be careful, kids. Use the negative button. Negative square root of 3 over plus I. You can do it, Jeff. I to the 8th power. Bam. And again, this is what 128 square root of 3 is.
I have a question.
Yeah.
Doesn't I disappear when it's when it's something like even power?
No, because you get middle terms.
If I squared, it's -1.
Totally. On the last term. Let me see. Well, it's not here, but when we did, all right. If you do, all right, let me see. Watch
Oh, never mind. Yeah, I got it.
the middle term is going to have the I left over, correct? The only time you're going to get rid of it and make it real is if it's complex, if it's conjugates, right? Where one's plus and one's minus, because then the middle term cancels. Okay, I like it. Oh my God. Okay, now, what time we got? Okay, one more thing here. This is such cool shit. I still remember when I first learned it. And by the way, let me show you something. I do not like this notation, Sam. I hate this notation. Cosine n theta plus I sine theta n theta. They just make it CIS, like that. It's their own little crime show. Isn't that the name of the thing? C, or is it C? I can't remember. Screw it. I just hate that. But I mean, if you like it, you see in the book, I mean, you can use it. It's in the book that I told you to buy or get or have access to. So I can't complain if you use it, but I just don't like it. Oh yeah, I forgot to tell you the name of this thing. Where do they have it here? Well, oh, that's the quotients. We're going to do that in a minute. You people. Here we go. Powers of complex numbers, de Moivre's theorem. So we basically just proved the way you say this guy's name is de Moivre. I love it. So de Moivre's theorem is right here. So what we just proved. This is the correct way to write it, and this is the bullshit way to write it. Just want to make sure you understand. So the next thing we're going to do is this. Doesn't that look yummy? All right, anyway, so let me see. Let me think. Okay, let's try to get this thing started. Let's do it. So now I'm going to try to take these roots of the complex number. So it's, how do I want to say this? Let me think. How much time we got? We got enough time. Okay. So I'm going to erase all this. Erase you. So let's go back. Let's start with our normal z little complex number a plus bi, which can represent as r cosine theta plus I sine theta. Jeff.
Professor,
Yes.
so off the camera.
What's up, sir?
I can't see it.
Oh, I'm sorry. That's right. I forgot. I sat down and did this. Okay. Let's start with a normal little, get up there. So what we want to figure out is, let's try something like z to the 1/2. So I want to do the square root of this. So this is the part that's going to be difficult, obviously, right? So let me see, how do I say this? Watch this, watch this. Okay. So if all right, let me see, how do I say this? If I did this, all right, let me see how I can say this. All right, so what would this be? So if r squared cosine 2 theta plus I sine 2 theta equals this, what is r squared times cosine theta plus I sine theta? I'm not sure if you guys are going to go with me on this. Let me see if you guys will go with me on this. I really, so look, r squared times cosine of twice theta plus I sine of twice theta equals this, correct? So what if I replace 2 theta with theta? What would this become? So if cosine of twice theta plus I sine twice theta becomes r cosine theta plus I sine theta.
Theta over 2.
Yeah, I don't know if everybody sees this. How do I write this? Oh, yeah. Square. So now if I do the square root, I basically get that. Now there's a little more to this story. Let me see. How do I want to go here? All right, I don't know if you guys really follow it. This is what we just showed earlier, right? This is what we just showed earlier. And then I said, oh, if I replace this with theta, then this has to be half of that. That's basically what this thing is saying. That is half of that. Bam. Cool. So then if I replace r squared with r, that becomes r to the 1/2. Now, the tricky part is, where do the other angles come from? So let me see. So this is a good place to start. I kind of want you guys to buy into this, because then I could just do the same thing. If I want to know what the 1/3 power would be, I could just put a cube here, and that would be 3, 3, and then I could just cut in thirds. I could do the same thing. Okay, maybe. All right, so I forgot. Oh, yeah. So let me ask you this. All right, if I write this, is that different from this? Are those different? Give me an angle. Give me any angle.
5/6.
5/6. If I add 2 pi to that, isn't it still pi/6? Does everybody understand that? So is there any difference between these two statements?
No.
I really want everybody to be on board with this. All right, I like it. There's not a damn thing different between these two statements. Right? Okay, I like it. So I can do what I just did. How am I going to marry these things? All right, this is going to be neat. So here, instead of, all right, let me see, let me try this. I'm going to erase this and we're going to kind of redo this. I wanted you to bind this piece first before I brought that weirdness in. But now what I can do is, if I say r cosine beta plus 2 pi k plus I sine beta plus 2 pi k squared. All right, how do I want to say this? Let's be getting a little messy. I'm trying, I don't know if you guys noticed, but I'm trying something new. I wanted to try a different way to prove this. This is getting, let me think. Is this gonna work? I think so. All right, let me do this. I'm not gonna make you wait for me to figure out the next step in this thing. I'm making up on the fly here. There's a standard way to prove this, and I'm trying to do it a different way. But let me show you where we're gonna head, where we're gonna lead to. And then I'll kind of figure out if I want to keep going. This is where we're headed, and it kind of makes sense. Like I said, it didn't have to be a square root I did. I could have done a 3rd root or a 4th root or anything. I would have just ended up dividing by that many times. And the 2k pi is kind of neat. Let me think. How do I? Can somebody tell me what's the how do I say this? All right. Can somebody tell me what are the answers to this? Get out of there. Well, sure. X squared equals 4.
Plus minus 2.
Yeah, so there's actually 2 answers to that, right? So that's all the roots of 4. So every square root is going to have kind of 2 answers to it. So what about this? What's wrong with this? How many answers should that have? No, come on. You could do better. What's the power on that problem?
2 answers.
Should have 3 answers, correct? I know the real answer is really easy to get, but you lost 2 complex answers. But stay with me, stay with me. All right, this is the last thing we're doing today, okay? I'll end up on a concrete thing that you guys will still hate anyway. How do I get the other 2 answers? I subtract the 8, and then I can factor this. No, Jeff. There you go. Right, and then I have to use, let me erase my craziness there. Okay. A quadratic formula to get the other 2 answers here, correct? You guys with me? Now stay with me. Trust me, just try to stay with me. Here we go. So I get x equals 2, and I get x equals negative b plus or minus the square root of b squared minus 4ac. What's that going to be? 4 minus 16 negative 12 over 2. Let's see, does that look good? B squared minus 4ac, yes. Okay. And that's gonna, so you can see why they didn't show up, because they are complex. I can take a 4 out, which becomes a 2. I can take an I out for the negative. And then what I have left is a 3. And so I get -1 plus or minus I rad 3. Does that look a little familiar, although just a little bit jumbled around? Does that look a little bit familiar to anybody? Isn't that almost the one we did earlier, except I had the rad 3 on the real part? Stay with me. This is so cool. I feel like I've lost everybody, which is too bad, except for Rio. I can see him. Is anybody else out there? Give me a thumbs up or something. Nobody else? Anybody else? There's Bowen. There's Charles. Isabel. Paul. I am. And well, that's all right. That's somebody. Okay. All right. Now stay with me. This is so freaking cool. This is too freaking cool. There's a few more people. Thank you for coming back into the room. Oh, that's okay. I see somebody else. Watch this. This is so cool. Here's one answer, 2, right? Didn't we get that answer? The answer was 2. Can somebody tell me, now stay with me, let's see if we can do this semi-quickly. Let me take the 2 answers over here. Well, -1 plus I rad 3 and -1 minus I rad 3. Can somebody tell me what the angle is for this? So like, remember, we have to do inverse tangent of y over x. And this is, it's back here, right?
2 pi over 3.
Yeah, 2 pi over 3. I like it. So, all right, no, all right, stay with me. Now, what about the other one? Inverse tangent of negative rad 3 over -1. And of course, -1, negative rad 3, it's going to be down here. And that is 4 pi over 3. Let me stop for a minute. So one answer is at 2. The next answer is 2 pi over 3 away, yes? The next answer is 2 pi over 3 away, and it's the point -1 plus I rad 3. Where's the next answer? How far away is the next answer? How far apart are these 2 angles? I really haven't drawn mine to scale too well, but oh well. Oh, let me try it. Oh, Jeff, come on, dude. It's okay. You'll be all right. You'll be all right. Let me try this again. 2 pi over 3 should be like there. That's a big difference there, buddy. I know. And then the next one, I've really lost everybody now. Oh, Jeff, you suck so bad. 4 pi over 3 is there. And how far apart are these 2? How far is 2 pi over 3 away from 4 pi over 3?
2 pi over 3.
2 pi over 3 away. And then how far away is it from 4 pi over 3 back to here?
2 pi over 3.
Okay, now, so when you take a cube root of any number, all right, no worries. When you take the cube root of any number, the answers all be 2 pi over 3 apart. They kind of cut the plane into 3 parts. And that's really what this is all about. It picks up these other answers. When I do this, it picks up the other answers. Oh man, that was a rough note to end on, but I think we're going to end there. All right, so tomorrow we'll finish the proof of this. We'll try some more specific examples out. Okay. And hopefully it'll make more sense after tomorrow. We'll find out. All right, guys, you're free to go. Let me know if you need to hang out. Otherwise, you can head out.
Thank you.
Sure.
Thank you.
Sure.
Thank you, Professor.
You're welcome. Everybody else is good? All right, I'm going to head out. I'll see you guys.